This is part 2 of the CHUMP project, Program EEPROM. This project employs the AT28C16 EEPROM chip as a stable memory module, providing essential storage for instructions and data while retaining its contents even without power. This electrically erasable programmable read-only memory, EEPROM, offers 16 kilobits of non-volatile storage organized as 2K by 8 bits, resulting in 2048 memory locations, each storing 1 byte of data. However, using a 4-bit address bus limits us to 16 unique 8-bit memory locations. Right now, I have Feinberg's code running on page 0 and the first 14 Fibonacci sequences in hex running on page 1 with the other two lines displaying FF because the rest of the Fibonacci sequences are above 255. The program EEPROM holds pre-flashed machine language code with outputs from the SN74LS161 program counter connected to the EEPROM's address pins for sequential instruction access. LEDs attached to the EEPROM's output pins provide visual confirmation of each accessed instruction. Each clock pulse advances the program counter, enabling the processor to fetch and execute machine code, manage control logic, and handle I/O tasks efficiently. In the CHUMP instruction set, each instruction is an 8-bit binary value where the high nibble is the opcode and the low nibble is the operand, distinguishing between constants and RAM addresses. There are two ways to program the EEPROM, one of which is manual. I use 11 switches for the 11-bit address capacity, allowing for 2048 memory locations. Each row is 8 bits long, and I use the first 16 locations along with 7 bits to simulate counting from 0 to 15 in hexadecimal. To change any of the 8 bits, I make RCLK through a switch high to start programming, set the desired bit to on, adjust the wires connected to the bar graph, and then briefly press the button before turning the switch back to low. Here I manually programmed the 7-segment display, counting from 0 to 15 in hexadecimal. A more efficient approach is through Arduino, which performs all the functions of the manual process, but with greater efficiency by utilizing shift registers. This code is based on Ben Eater's code, but I've introduced some specific modifications that I'll outline here. In my code, I added 3 separate arrays, data page 0, data page 1, and 7-seg code, each containing unique data to be programmed into different EEPROM pages. The 7-seg code array is always programmed into page 0 via this program 7-seg codes function, which specifically writes the 7-segment display codes into page 0 of the EEPROM. This setup enables the display to show the hex value of either the high nibble, the 4 leftmost bits, or the low nibble, the 4 rightmost bits. By setting the only program 7-seg codes flag to true, the code programs only the 7-segment codes. If the flag is false, the code first erases the EEPROM and then programs data page 0 and data page 1 into separate pages. This structured approach is ideal for handling multiple data blocks and selectively programming the EEPROM. The program page function further streamlines programming different pages in the EEPROM. It takes a page number and a data array as arguments, calculates the starting address for that page, and writes the entire page using a loop. Pointers are used in the program page function to efficiently pass the memory address of an array, like data page 0 or data page 1, rather than copying all of its data, making memory usage more efficient. The byte star data pointer in program page points to the first element of the array, allowing direct access to each element for programming the EEPROM without the need for duplication. This way, when you call program page 0 data page 0, only the memory address of data page 0 is passed, allowing program page function to write each byte from the original array directly to the EEPROM. Here are the 7-seg EEPROMs being programmed, as well as the main EEPROM. Thanks for watching.